Hello and welcome to INE's CCI Service Provider version 5 Learning Path. Today in this course we will talk about BGP attributes, where we will talk about a specific attribute which is going to be local preference. So local preference is the second attribute from the attribute list. If you remember, we had wait, which was the first attribute in the attribute list of BGP. Wait was the most influential attribute, which was Cisco proprietary. After wait was local preference, then we had the locally originated, we had AS path, we had origin, we had MED, we had eBGP preferred over iBGP, and then we had the closest IGP neighbor, iBGP neighbor, and then we had the oldest neighbor, and then router ID. So today we would talk about purely local preference. If you remember, local preference is a well-known attribute. However, it is not mandatory, it is discretionary, which means that if it is present in the update, it does not need to be present. But if it is configured, every BGP implementation would understand local preference, whether it's a Cisco router or a Juniper router. It doesn't really matter because it's well-known and discretionary. Now, something about local preference: higher is better, default is 100. Local preference cannot be advertised outbound across an AS. It can be advertised outbound within an AS. So if I have to configure local preference, I can configure inbound from an AS, but I cannot configure outbound to an AS. You can do outbound only within the AS. That's why local preference is non-transitive. It's non-transitive. The definition of transitive is that it can be sent across multiple ASs. So to demonstrate local preference, we would use this diagram here. I have approximately 6 routers here. All the routers are iOS XZ except for router 3, which is going to be XR 3 router. So this is the router which is going to be XR. All the remaining routers are iOS XZ. So we will basically build a BGP neighborship between 1 and 2, between 1 and 3, which is XR 3. We will also build a neighborship between 2 and 4, 4 and 5, 5 and 6, and 3 and 6. We would build the neighborship on the directly connected interface. Since I'm not running any kind of IGP at this point of time, so I would not build the neighborship on the loopback. I would just build the neighborship on my directly connected interfaces. Once I establish the neighborship, let's look at how R1 goes to destination R5's loopback. We would advertise R5's loopback in BGP. So from R1's perspective, he has 2 paths to go out of the AS. He could exit out from R2 or he could exit out from R3. So if we want R1 to exit out from R2, I could configure a local preference on R2 inbound from R4. I cannot configure R4 outbound to send a local preference to R2, but I can configure R2 inbound. So when I receive the update from R4, he would set the local preference so that he can send it to all his neighbors internally. There is no BGP neighborship between 2 and XR3. I would only form neighbors from R2 to R1 and XR3 to R1. So if I set the local preference on R2, R1 should automatically prefer R2. Once we do that, we would also try and change the local preference on XR3 so that R1 now shifts to XR3 as a preference. So let's go and do this. Let's first build the BGP neighborship. As of right now, only IP addressing has been pre-configured. We have not really built the BGP. So we will first build the BGP and see how router 1 is going to router 5's loopback. So let's go and build this. So let's start off with all the external ASs. So we'll start with 4, 5, and then 6, and then build AS1. So our 4 is going to be neighbors with router 5 and router 2. And the autonomous system was 2. Neighbor would be 20.2.4.2, which is R2. Remote AS would be 1. The second neighbor would be 20.4.5.5, which is R5. remote AS would be 3. And let's go to 5 as well. On 5, he would establish adjacency or BGP neighborship, eBGP neighborship with 4 and 6. So router BGP AS number would be 3, neighbor 20.4.5.4, remote AS would be 2, and neighbor 20.5.6.6, remote AS would be 4. Let's also advertise my loopback. So 5.5.5.5, mask would be 255.255.255.255. Let's also create another loopback, maybe loopback 55, and advertise that also in BGP. So network 55, 55, 55, 55, mask 255, 255, 255, 255. So at this point of time, my neighborship between 4 and 5 is up and running. R4 should have received the routes of R5, both the loopbacks, show IP BGP. I should have both the loopbacks in my BGP table. Let's go back to 5 and check show IP BGP summary if my BGP neighborship is up. So it is up with R4. And let's check my BGP if I have both the loopbacks being advertised. Let's do a show IP interface brief. They should be advertised exactly how it's in the routing table. I believe they are /32. So both the loopbacks should be advertised to R4. So they are now in the BGP table. It just takes a bit of time. Let's also build the neighborship on R6 with 5 and XR3. So R6 would be in the BGP AS4, which you can see as per this diagram. R6 is in AS4. So neighbor would be 20.5.6.5, which is R5, remote AS3. The second neighbor would be XR3, which is 20.6.19.20. Remote AS is 1. So again, now R6 should have established adjacency or BGP neighborship, eBGP neighborship with R5. He should learn both the loopbacks of R5, which is in his BGP table. So basically, now I have configured AS2, 3, and 4 is basically configured. All we need to do now is configure AS1. So let's start with router 1, which is again an iOS XZ router. So router BGP 1, neighbor would be 10.1.2.2, which is R2, remote AS1. Let's also advertise my loopback 1111, mask 255.255.255.255. And my second neighbor would be XR3, which is going to be 10.1.20.20, remote AS1. Let's now configure R2. So router BGP 1, neighbor, I have one iBGP neighbor, which is R1, and one eBGP neighbor. Towards the iBGP, I should do a next hop self because I don't have any kind of IGP running at this point of time. So router 1 would receive the route from R4, from basically R2, because R4 gives the route to R2. That's an eBGP connection. When R2 gives the route to R1, R1 would see the next hop as router 4, and he does not have reachability to router 4 because of any kind of IGP not running. So router 1 would not be able to install that route in the BGP table. In fact, in the routing table. It would be in the BGP table as valid, it would not be best. So let's first build the neighbors, and then we'll fix the next hop issues. So neighbor would be 10.1.2.1, remote AS1. So I should now form adjacency or BGP neighborship should be established between router 1 and router 2. Let's also build the eBGP between 2 and 4. So 20.2.4.4 remote AS2. So now R2 should establish both his BGP neighbors. Show IP BGP summary should show me that I have both my BGP neighbors up and running. So you can always look at show BGP IP BGP summary. If your state is basically blank, it means your BGP neighborship is up. Or you could do a show IP BGP neighbors, include BGP state, which shows me my, I think it's state, which shows me that my state is up, it's established. So you just have to give it in the right format. It's lowercase. So my BGP neighborship is up and running with both my neighbors. So R2 should have learned R5's loopback through R4 at this point of time. For him, the route is valid and best because for him, the next hop is reachable. Now, from R1's perspective, he receives the route from R2 about R5, but for him, the next hop is not reachable. If you remember from the rules perspective, what's happening behind the scenes? So R5 is giving the update to router 4. That's an eBGP neighborship. So R5 prepends his own AS, which is the default rule for BGP. When you give the update to an eBGP neighbor, you prepend your own AS. So R5 prepends his own AS and sets the next hop to himself and also sets the origin, because all these three attributes, AS path, your next hop, and origin, they are well-known mandatory attributes. So R5 sets the AS path to AS3, sets the next hop to himself, and sets the origin as I, because we have advertised the loopback using a network statement. When R4 gets it, before he accepts the route in the BGP table, he needs to perform some checks. The first check is going to be that, does the AS path contain my own AS? No. The second check is going to be, does the update contain all the well-known attributes? Because all these three attributes must be present in the BGP update. So does it contain AS path? Yes. Does it contain next hop? Yes. Does it contain the origin? Yes. So if both these conditions are met, the first condition was that I should have all these three attributes in the update. That condition is true, it is present. The second condition was that the AS path should not contain my own AS. So what is the AS path R4 seeing? R4 is basically seeing the AS path as 3, correct? Is it my own AS? No. So he accepts the update in the BGP table. Now from the BGP table to go in the routing table, it performs one more check. Is the next hop reachable? Now for R4, the BGP neighborship was a directly connected neighbor. So for R4, the next hop, which is 20.4.5.5, it is reachable. So now R4 puts that route in the routing table. Whatever is in the routing table, routes in BGP can only be advertised what's in the routing table. You will never advertise what's in your BGP table. You will always advertise what's in your routing table. So once the route goes in the routing table of R4, R4 advertises to R2. R2 performs the same checks that does it contain the three well-known mandatory attributes, AS path, next hop, origin? Yes. Does it contain my own AS? No. So he accepts the update in the BGP table. R2 would see the AS path as 2-3 because R4 was prepending his own AS. And now when R2 has to give the update to his neighbor, he has to first put the route in the routing table. Would he put the route in the routing table? Yes, because for R2, the next hop is reachable because R4 had put himself as next hop. It's an eBGP update. However, when R2 gives the update to an iBGP neighbor, which is router 1, he does not prepend the own AS. He does not prepend his own AS. And he does not change the next hop. So when R1 gets the update, he performs a check. That does it contain all the three well-known attributes? Yes, it contains AS path, which is 2 and 3. It contains next hop, and it contains origin. Does it contain my own AS? No. So both the conditions are met. R1 accepts the route in the BGP table. Now, which you can see on R1, I have both the routes in my BGP table. Now for R1 to put that route in the routing table, it needs to perform one more check. That check is going to be, is the next hop reachable? What's the next hop? It's 20.2.4.4. Do I have that route in the routing table? Is that reachable? No, because I'm not running any kind of IGP. So since the route is not reachable, R1 would not put that route in the routing table. So basically for R1, that route is not reachable. If I check my routing table, show IP route, and check, I do not have 5555 and I do not have 55, 55, 55, 55. I don't have that route. So obviously for R1 to put the route in the routing table, what do I need? I need to fix the next hop issue. So just remember, as a thumb rule, if you have an eBGP neighbor and an iBGP neighbor, do next hop self towards the iBGP neighbor. If you have only eBGPs, you don't need to worry about next hop. But if you have only iBGP, you don't need to worry about next hop. But if you have an eBGP and an iBGP neighbor, you should do a next hop self towards the iBGP neighbor, unless that next hop was reachable through some other kind of protocol. So one way to fix this would be either I go to R2 and do a next hop self towards R1. That's one way. Is there another way to fix this? Think about it. Is there another way? Let's say if the question said, do not use next hop self command in the lab exam. What do I do in that case? Maybe I could go and advertise that link between 2 and 4 in some kind of IGP. If there was an IGP running in AS1, if there was some kind of IGP running between 1 and 2, then I could maybe advertise that WAN link in IGP. Another way could be, maybe I advertise that WAN link in BGP. So if I don't want to give next hop, I could go to R2. Instead of doing next hop self, I could just advertise that WAN link between 2 and 4 in BGP using a network statement. In that case, R1 gets the WAN link through BGP. So he does a recursive lookup and he has the route. So he would put the route in the routing table. That's another way to achieve that. There could be another way also to fix this issue where, let's say the question says, do not advertise this route in any IGP, do not redistribute this route in any IGP, do not advertise this route in BGP, or do not redistribute in BGP, and do not use next hop self. What do I do in that case? What I could do is I could use a route map. So on R2, I could use a route map which says, set IP next hop to my own IP. So R2 would say, let's set the IP to 10.1.2.2, which is my own IP, and attach that route map outbound to R1. So when I send an update to R1, I will check for the route map, and the route map is going to set the next hop to his own IP. That way R1 would see next hop as router 2. So many ways of fixing your next hop issues. Let's try this with a route map. So maybe on R2, I will fix the next hop issue towards R1 with a route map. And maybe on the XR, I will fix the next hop issue towards R1 using a next hop self. Just different ways of doing it. It all depends on the requirement of the question. It all depends on what limitations you have. If there are no limitations, you could do whatever you want. You could do a next hop self. Try and avoid advertising that link in IGP or BGP because you don't want your IGP to change. So either use a next hop self or a route map or a route policy on XR routers. So let's try and do this. I'm going to go back to router 2 and towards my iBGP neighbor, which is R1, I would say neighbor 10.1.2.1 route map to R1 outbound. So when I send any updates to this neighbor, check for this route map to underscore R1 outbound. Let's create this route map, and the route map would say to R1 permit sequence number 10. I don't need to match anything because all the routes being sent to R1 would check for this route map. I'm not matching a specific route only. So I'm not matching anything. I would just say set IP next hop to 10.1.2.2, which is my own IP. The effect of this you would see on router 1. Let's go to router 1 and do a show IP BGP. My next hop should now change from 4 to R2's IP. Let's wait. We can always do a clear for it to take effect. Let's do a clear IP BGP star soft, and same thing on R1. A clear IP BGP star soft, and let's try again. Show IP BGP. What's my next hop now? It is 10.1.2.2, which is R2. And since that next hop is directly connected to R1, next hop is reachable. So that route now becomes best and goes in the routing table. Show IP route, I would now see that route 5555 and 55 in the routing table learned from BGP. Let's now configure R1 and XR1 as my BGP neighborship. So let's go back to XR3 and run BGP here also. Router BGP1. Let's activate address family IPv4 unicast, and if I want to advertise some routes, I could advertise some routes with a network statement here, but I'm not advertising any of my loopbacks as of right now. Just enable the address family, exit out. Neighbor is going to be, I have two neighbors, one eBGP, one iBGP. So neighbor would be 10.1.20.1. Remote AS would be 1. Do I need update source? No, because I'm not using the loopback for my neighborship. I'm using the directly connected interface. Do I need to change my eBGP multi-hop? No, again, it's an iBGP neighborship. So I don't really need to change my eBGP multi-hop also. Default is 255 for iBGP. For eBGP, it was 1. So if I was forming neighborship between two routers, which were basically eBGP neighbors, and if I was forming on the loopback, then yes, I would need to give update source also, and eBGP multi-hop need to be changed from 1 because the default for eBGP is 1. So change that from 1 to maybe a higher value. So all I do is the neighbor command, activate my address family, IPv4, unicast, and let's do a commit. So if I go back to R1 and do a show IP BGP summary, I should see my BGP neighborship with XR1 coming up. Let's verify on XR3, show run router BGP. So I don't see the address family, in fact, inside my neighbor command. Let's go back and re-give it, because you have to activate the address family, only then your neighborship would come up. So neighbor, address family IPv4, unicast, and let's do a commit. Let's verify my config. So now I do see the address family, and verify if the neighborship has come up between router 1 and XR3. Let's check the show IP BGP neighbors. 10.1.20.20. So what do I see here? It's an active. Let's do a show IP interface brief just to verify my IP address, 10.1.20.1, and XR1 ping 10.1.20.1. So I'm not able to ping show run interface. I don't have the interface that really connects towards router 1. Let's create that interface. That's why my BGP is not coming up. So interface gig 0000.120. Encapsulation would be the1Q 120, and IPv4 address would be 10.1.20 dot 20 to 55 to 55 to 550. Let's do a commit. And let's do a ping. So now I do have reachability. If I check my router 1, my BGP should come up. So I see open sent now, which is a good sign. My BGP neighborship is now up and running. But again, as of right now, I really haven't formed BGP neighborship between XR3 and R6. I haven't formed that neighbors yet, so we need to establish that neighbor also. And again, because XR3 would have an eBGP and an iBGP, I should fix the next hop issue towards R1. So let me go back to XR3 and go under my BGP. So router BGP1 neighbor 10.1.20.1, and here I would say next hop. So that should be under my address family. And next hop self. Let's also build the eBGP neighborship between XR3 and R6. So that's going to be neighbor 20.6.19.6. Remote AS was 4. And address family IPv4 unicast. Should be under the neighbor. And let's do a commit. So it really doesn't let you go give the address family first. It's kind of finicky because you just have to give the neighbor command first with the remote AS, do a commit, and then go back and do your address family. So if you actually look at this, it's throwing me out to, once I give the address family inside the neighbor command, it still throws me out to address family global one. So I'm going to go back to my neighbor now. And so I'm inside the neighbor. And let's give address family IPv4 and do a commit. Let's check show run router BGP. So I still don't see the address family inside the neighbor. Let's go back. Router BGP1 and give the neighbor and say address family IPv4 unicast. So now I am inside the neighbor. So address family inside the neighbor. Let's do a commit. So show run router BGP. I should now establish an eBGP neighborship with R6. Let's check my neighborship between 6 and XR3. It has come up. Show IP BGP summary. I have my BGP neighborship up and running. Now, is XR3, does he have all the routes in his routing table? Would he have the routes? Let's check. Show BGP IPv4 unicast. So XR3 has the routes of router 1, but for some reason he does not have the routes from R6. So what's actually happening is that R5 is giving the routes to 4 and to 6. 4 gives the route to 2, 2 gives the route to 1, correct? Would 1 give it to XR3? No, because of split horizon rule of BGP. So maybe R1 needs to be a route reflector, only then R1 would give the routes to XR3. However, shouldn't XR3 receive the route from R6? He should have, right? But in iOS XR, if it's an eBGP connection, you require a route policy, because without that, I would basically drop all routes learned from an eBGP neighbor. So it's not that R6 is not sending the routes. R6 is advertising both the loopbacks. Let's in fact verify that. If I go back to R6 and do a show IP BGP neighbor 20.6.19.20 advertise routes, I am advertising 5555 and 55 to XR3. But XR3 is basically not accepting the route in his table. He discards the route. Let's do a debug BGP IP. Let's do a debug BGP. My neighbor was let's do it specifically for maybe an update. I could be specific to a neighbor, but I'll just say debug BGP update. And let's see, let's do maybe a clear on R6, clear IP BGP star soft, just so that he re-advertises the route. Now, the XR routers sometimes, depending on the platform, like if it's a virtual router, it really doesn't show you the debugs. At least on the physical router it does, but these routers are not going to show me. So in the lab exam, if you just want to verify something, don't try and use a debug. Try maybe using a show command. Let me do an annul. So let's do undebug BGP. And let's see why XR3 is not accepting the route. So for me, because it's an eBGP connection, there's a built-in, like a kind of a route policy which basically blocks everything. So if you receive any update from an eBGP neighbor, he would basically not accept the route. So what do I need? I need to create a route policy. The route policy could just be a pass. I don't need to match anything at this point of time. So let's create one. Route policy, pass, and the condition would just be pass and policy. A pretty straightforward, simple policy is what I'm creating right now. Let's go back to router BGP 1 and neighbor 20.6.19.6 to this neighbor under my address family IPv4. I would say route policy pass in. So when I receive updates, check for this route policy, and when I send updates outbound, check for this policy again. Because again, if it's an eBGP neighbor, XR3 would not send any updates to you. He would not accept any updates from you by default if it's an eBGP. iBGP, no problem. I would send him routes. I will receive routes from him. Absolutely no problem. But for eBGP, you require a route policy. Let's do a commit. Once I do a commit, he should accept the routes. Let's do a show BGP IPv4 unicast. So now he has the routes from R6. He's receiving the routes 5 and 55. Would he give the routes to R1? Yes. Would R1 accept the route from him? No. I mean, R1 would accept the route in the BGP table, but he would never put the route in the routing table because the next hop is not reachable. If I check on R1, show IP BGP, what's my next hop? So I see 10.1.2020. This is because I gave the next hop self command. If I had not given the next hop self, R1 would accept the route in the BGP table, but would never put the route in the routing table. But because I fixed the next hop on both the edge routers, R2 is doing a route map towards R1 and fixing the next hop. XR3 is doing a next hop self towards R1 and fixing the next hop. So now R1 receives the routes from both of them and the next hop is reachable. He would put the route in the routing table. Now, which one does he put in the routing table? Only the best path. BGP does not do load balancing, right? Because BGP has maximum path as 1. So only one path goes in the routing table. Which one? As you can see here, he put the route through R2, not through XR3. Why is that? Have I configured wait on R1? No. Wait is by default 0 because it's not a local route for R1. He has learned the route from someone else. Wait by default is going to be 0 for BGP learned routes and it's going to be 32768 if it is local route. So is the route local? No. He has learned from two neighbors, right? Weight is 0, same. Local preference, default is 100. We haven't really set local preference. So even that's the same. It's not locally originated. So even that's same. AS path, if he goes from XR3, it's 2 hops away. If he goes from R2, it's 2 hops away. AS path is also the same. What's next? Origin. Both the neighbors, both the edge routers are advertising the origin as I. So that's the same. I is IGP and question mark is incomplete. Because I advertise the loopbacks of R5 using a network statement, the origin shows as I. That's the same. What's next? Med. Did I configure med? No, it's 0. What's next? eBGP preferred over iBGP. Both my neighbors are iBGP neighbors from R1's perspective. R2 is an iBGP neighbor, XR3 is an iBGP neighbor. That's the same. What's next? Technically, it should be closest iBGP neighbor or your BGP neighbor and then oldest neighbor. But those two they are basically eliminated. It doesn't look at that. It goes straight after eBGP preferred over iBGP, it goes straight to router ID. What is the router ID of R2? It's lower than XR3. That's why R1 is preferring R2, not XR3, because lower router ID wins over higher router ID. All the previous attributes were the same. Now I want that traffic should go, as of right now, it is going from where? It is going from R2, right? Which we can see it's the best path. So if I look at my routing table, show IP route, it is choosing R2. Now I need that all traffic may be destined for 5555 should go from XR1. All other traffic should go from maybe R2. All other traffic. And I want to use local preference. So let's do local preference on both the routers. So R2 would not send a local preference to R1 for 5555. He'll keep it as default, 100. XR3 would send a higher local preference for 5555. And for the other routes, for 55, XR3 would send the default local preference, which is by default 100, but R2 would send a higher local preference. The effect of this would be that R1 would choose R2 for 55, and he would choose XR3 for 5. Let's try and do this. So I would go to router 2 first, and let's configure router 2. So let's create an access list that matches 5. So access list 1, permit 5555, and create a route map 2. I think we already have a route map towards R1, so I have to reuse the same route map because you can only apply one route map in one direction. So I'll have to reuse the same route map, R1 I believe it was, 2_R1, and say permit sequence number 10. If this matches, match IP address 1. It's a permit, I'm not filtering it. I'm still sending the route. Set the local preference, or I can leave it as default. I don't have to do really anything. Keep it as default. And then let's do a permit 10,000. And this would be set local preference 10, or let's say 122, higher than 100. So what have I done? Show run section route map. I have said if this matches, I should in fact now go and attach this to my second statement also, otherwise only the first route would have the next hop. Earlier it didn't matter because we were just changing the next hop. Let me go and change this also. Sequence number 10 and set the next hop here also. So let's go back and check. So what am I saying? If this access list matches, which is 5555, if it matches, send the route, because I have a permit statement here, send the route, but Only change the next hop. Don't do anything else. So whatever's the default local preference, that would be sent. All other routes, change the next hop to yourself and set the local preference also. What's the effect going to be? Let's do a clear IP BGP star soft. The effect of this on R1, if I do a show IP BGP, I should see for 55, I'm seeing 122. But for the other routes, 5555, I'm still seeing it as 100, which is default. So for all the other routes, R2 would send 122, except for 5555, which doesn't get filtered. He still sends the route with the default local preference, and he just changes the next hop. Correct? So now all destinations except 5555 would be going through R2. Now we go to XR 3. So here, I would create a route policy to match that specific prefix for who we want to change. Now, I could do a route policy without a prefix set, like how on router 2, I made an access list to match 5555. Similarly here, I could match 5555 directly inside my route policy by giving the command if destination includes open parentheses and say 5555, then do this. Or I could use a prefix set. If you had like multiple routes, you could use a prefix set. Let's try with the prefix set this time. So let's do prefix set. Let's name this R5 loopback 0 and give 55.5.5.5/32. And let's do end set. Let's create a new route policy to router 1. And here my condition is going to be if destination includes my prefix set, which was R5 loopback 0, then what do I need to do? I would set the local preference, right? Set local preference to, let's say, 200. But don't forget, like how in route maps we did permit 10,000. There was another route map which said permit 10,000 for remaining routes. If I don't do else, all remaining routes would get filtered. So I should say else pass. Don't do anything, just pass the routes. Okay, and let's do end if and end policy. Let's do a commit. Let me show you my route policy now. Show run route policy, which would be to R1. So this is my route policy, which calls for a prefix set, which basically like an access list that matches 5555. So if that route matches, set the local preference to 200. Else, send the route as it is, whatever the route has. And end if end policy. Now let's go to show run router BGP. If you remember, we had a route policy. We don't have a route policy towards R1. I'm going to now send the route policy towards R1. So let's go to neighbor, router BGP. I could do outbound towards R1. I really prefer doing inbound from the eBGP neighbor. There's a big difference. So if I attach the route policy towards R1, it has to be outbound. The problem in doing that is, imagine if I had 10 neighbors, 10 iBGP neighbors. I have to do individually to each one of them. Instead, what I could do is when I receive the route from the eBGP neighbor, I change the local preference and my BGP table changes. In that case, I would automatically send the new local preference to all my neighbors. It just makes it easier. So let's attach it inbound here. Now you can only apply one route policy to that neighbor. So I'm going to remove the pass in, and instead of that attach the policy that I created. So obviously my name is now wrong because I used the name 2_R1, but doesn't really matter. It should still work. That's just a name, route policy name. Obviously you should use relevant names just not to confuse yourself in the lab exam. So router 1, neighbor. So I could remove this pass and attach it inbound, or I could do it towards this neighbor outbound. Like I said, always try and do it inbound because then you don't have to do it towards all your neighbors. In our case, we only have one neighbor, one IBGP neighbor, so I could do it outbound also. Let me go to 10.1.2.1, which is my IBGP neighbor, address family IPv4, unicast, and say route policy 2_R1 out. Let's do a commit. Let's do a show run or show configuration failed. So what do I see? It says BGP detected the warning condition neighbor does not exist. So let's go back. I gave 10.1.2.1, which is the wrong neighbor. Let's exit out. Router BGP1. And neighbor was 10.1.20.1. I believe that was the neighbor. Let's verify. 10.1.21. Address family IPv4 unicast, and let's give the route policy commit. Let's go back to R1 and verify his BGP table. So now, if you see, for 5555, he is preferring XR3 because the local preference is 200. For other routes, which is like 55, XR1 or XR3 is sending 100, but R2 is sending 122. Higher is better. So for all destinations except 5555, I would go through R2. I would exit the AS through R2. And for destination 5.5.5.5, I would exit through XR3. So you see, I can use local preference to do path manipulations, and local preference is pretty high up in the order. The only attribute before local preference is wait. So if wait is not configured, then local preference would be the best choice. Only one thing to remember is you can never send local preference outbound across an eBGP neighbor. You can do inbound from an eBGP neighbor, or you could do outbound to an IBGP neighbor. I hope this video was informative to you, and thank you for viewing.